On August 15, 1977, a solitary 72-second burst at 1,420 megahertz forever altered SETI history, an unexplained signal hastily annotated WOW by astronomer Jerry Emin, never to be detected again. Officially, it remains classified as an unsolved anomaly, but now, researcher Avi Loeb claims that today's interstellar Comet 3 I/Atlas occupied that precise celestial position on that very same night, with orbital calculations placing the odds of such a coincidence at less than 1%. If a 2-gigawatt signal truly originated from 600 astronomical units away, what kind of intelligence or technology could possibly have transmitted it? The assertion is audacious, the evidence perplexing, and the implications staggering. Are we finally confronting the hidden truth behind the WOW signal? Or are we merely pulling at a cosmic thread that threatens to unravel everything we thought we understood? The Big Ear radio telescope swept across the heavens on August 15, 1977, recording a 72-second spike at 1,420 megahertz, the frequency of neutral hydrogen, the most abundant element in the universe and a natural target for SETI searches. The signal, captured as a string of alphanumeric characters, 6EQJ5, stood out dramatically against the usual background noise, peaking at a signal-to-noise ratio approaching 30:1. The printout, later annotated with a red WOW by astronomer Jerry Emin, became an instant icon in the search for extraterrestrial intelligence. The event's coordinates: right ascension 19 hours 25 minutes and declination minus 27 degrees, pointed toward Sagittarius, a densely populated region near the galactic plane. Big Ear's design permitted observation of only a narrow slice of sky at any given moment, and the signal occupied a single beam as Earth's rotation carried the telescope's field of view across the source. The match between the signal's duration, just over 1 minute, and the expected transit time for a fixed-point source through the beam was perfect. Crucially, no corresponding signal appeared in the second beam, effectively ruling out most forms of terrestrial interference. Frequency analysis pinpointed the burst at 1,420.456 megahertz, positioned just above the hydrogen line, with an offset of approximately 50 kilohertz. While this deviation is sometimes cited as a possible Doppler blue shift, the channel bandwidth and absence of high-resolution spectral data leave the true velocity interpretation ambiguous. The equipment's channelization established the constraints: 50 channels, each 10 kilohertz wide, with the WOW burst peaking in 2 adjacent bins. No raw intermediate frequency data or analog-to-digital record survived. Only the digitized summary, preserved in print and subsequent scans, remains. Follow-up scans of the same coordinates yielded nothing. The sky remained obstinately silent. Emin and the Big Ear team meticulously examined every available log, cross-referencing known satellites, aircraft, and local radio interference sources. No explanation proved satisfactory. The event's singularity, never repeated, never adequately explained, became the defining enigma of SETI's archival record. The WOW signal's data, frozen in those columns of numbers, remains the foundation for every probability calculation and orbital hypothesis that has followed. Avi Loeb's calculations begin with a deceptively simple question: what are the odds that Comet 3 I/Atlas, an interstellar object discovered in 2025, happened to align with the WOW signal's patch of sky on the same night in 1977? To answer this, Loeb's team extrapolated the orbit of 3 I/Atlas backward nearly half a century. The result: on August 15, 1977, the object would have been approximately 600 astronomical units from Earth, near right ascension 19 hours 40 minutes and declination minus 19 degrees. The WOW signal itself was logged at right ascension 19 hours 25 minutes, declination minus 27 degrees. On a celestial map, that represents a modest offset, but in astronomical terms, it's remarkably close enough to raise serious questions. Loeb frames the probability of the spatial overlap as less than 1%, comparable to flipping a coin and getting heads 7 consecutive times. Not impossible, certainly, but exceedingly rare. The calculation compares the sky area swept by a random interstellar object to the WOW signal's error box, factoring in the immense expanse of the celestial sphere. The sensitivity is striking. Shift the coordinates by just 1 degree, and the odds change dramatically. Loeb's critics note that orbital uncertainties in beam geometry could either widen or narrow the match, but the raw figure remains under 1% by his estimation. Translating the wow signal's intensity into transmitter power, Loeb employs a detected flux of 54 to 212 Janskis at Earth, at a distance of 600 astronomical units. This requires a transmitter, output between half a gigawatt and 2 gigawatts, depending on assumptions, comparable to the output of a large nuclear power plant. This isn't some modest beacon. It represents industrial-scale power, yet not beyond known technology. The numbers, Loeb argues, accumulate into a coincidence that demands serious attention. Most astronomers remain skeptical, cautioning that rare alignments do occur in a universe this vast. But the combination of orbital overlap and required transmitter power is sufficient to sustain the debate and to drive new searches for signals from 3i/Atlas as it traverses the inner solar system. For Loeb, the real test is whether future observations will deliver repeat detection or leave the wow signal as a singular enigma. Trajectory maps for 3i/Atlas reveal a path that defies conventional expectations. Instead of plunging to the solar system at a steep angle, as most interstellar visitors do, Atlas threads through the ecliptic, the same flat plane traced by Earth and its planetary neighbors. Its inclination sits just 5 degrees off level. For a body arriving from the depths of interstellar space, this represents an extraordinarily rare alignment. Dynamicists at the Minor Planet Center have run extensive calculations. Out of the infinite directions an object could approach from, only approximately 1 in 500 would land this close to the solar system's disk. The geometry is unforgiving. Most comets and asteroids, whether local or foreign, tilt and twist through space, their orbits shaped by ancient collisions and planetary gravitational perturbations. Atlas glides almost parallel to the planetary corridor, following a route more typical of native solar system bodies than cosmic drifters. The improbability compounds as the timeline tightens. Over the span of mere weeks, Atlas strings together a series of planetary near approaches. On October 3rd, it will sweep within 29 million kilometers of Mars, a margin that, by interplanetary standards, qualifies as a close encounter. Shortly thereafter, the orbit brings it within striking distance of both Venus and Jupiter, creating a sequence of close approaches that orbital statisticians are quick to flag as anomalous. For a random interstellar object, the odds of threading this multi-planet gauntlet are vanishingly small. Models from the JPL Solar System Dynamics Group estimate the compounded probability at less than 1 in 20,000. These are not the numbers that arise by chance in a sky populated with billions of possibilities. Statisticians brought in to audit the scenario emphasize the distinction between rare and impossible. In a universe this vast, low-probability events do occur. Yet when so many alignments converge, ecliptic-hugging inclination, a parade of planetary close passes, all within a single inbound trajectory, the pattern becomes conspicuous. To visualize these odds, imagine shuffling a standard deck of cards and drawing the ace of spades 5 times consecutively. Not impossible, but sufficient to make even an experienced card player pause and reconsider. Simulations run on supercomputers at the Harvard-Smithsonian Center for Astrophysics trace thousands of hypothetical interstellar visitors through the solar system. The vast majority slice through at steep angles, missing planets by tens or hundreds of millions of kilometers, never aligning with the ecliptic, never replicating the Atlas pattern. Only a handful in millions of runs reproduce anything approximating this geometry. The data points are unambiguous. Atlas is not following the script written by population statistics or random sampling. For now, the orbit stands as a statistical outlier. The rarity of the trajectory, the precise timing of the planetary flybys, and the low inclination all combine to set Atlas apart from the background noise of cosmic wanderers. Whether this pattern is a product of unknown natural processes or something else entirely remains an open question. But for the teams tracking Atlas, the numbers alone justify intensified scrutiny. The first images of 3i/Atlas forced analysts to fundamentally rethink their interpretations. Instead of the classic comet tail trailing away from the sun, a concentrated glow appeared on the forward, sunward side, a feature observers termed an anti-tail. This brightness, aligned almost head-on, resisted every correction for image smear or instrumental artifacts. Imaging teams at Gemini South and the Very Large Telescope compared their findings. A forward-facing structure should be exceptionally rare unless the nucleus is either non-rotating, tidally locked, or actively maintaining orientation. For a natural object, such stability is highly unusual. Some researchers argue for geometric explanations. Others suggest a controlled or at least non-random surface state. Momentum accounting deepened the puzzle considerably. As the comet approached the inner solar system, gas production climbed to approximately 150 kilograms per second, a robust outflow, sufficient to strip away over 12,000 tons per day. In cometary science, this kind of mass loss acts like a rocket engine. Jets of gas push against the nucleus, nudging its orbit away from the path predicted by pure gravitational mechanics. For typical comets, even modest activity leaves a distinctive fingerprint in the astrometric record, a gradual drift, a subtle curve away from Newtonian predictions. But dynamical modelers tracking 3I/Atlas found no such deviation. The orbit adhered to the gravitational script with uncanny precision. Monte Carlo simulations swept through every plausible combination of nuclear size and density. For anything smaller than approximately 5 kilometers across, the mathematics failed to reconcile. Atlas should have veered off course long ago. The only way to balance the equations: assign the nucleus a mass of at least 33 billion tons, likely more. That figure anchors Atlas in the record books as the most massive interstellar object ever detected, by orders of magnitude. Spectroscopists turned to chemistry for answers. Early spectra, though still awaiting peer-reviewed publication, circulated among research teams. The preliminary reports indicated an atmosphere dominated by carbon dioxide, possibly as high as 95%, while water vapor, the staple of most solar system comets, barely register above 5%. Such a ratio is not merely rare. It's almost unprecedented in local cometary science. A steep rise in cyanide emissions and a pronounced green coma added to the catalog of oddities. But the real controversy ignited around the metal emission lines. Neutral nickel appeared prominently in emission spectra, while iron lines remained stubbornly absent. In natural comets, nickel and iron travel together, forged in similar proportions in stellar furnaces, and released together during cometary outgassing. The absence of iron paired with a strong nickel signature raised speculative discussion of nickel carbonyl, a compound more familiar to industrial chemists than planetary scientists. One spectroscopist characterized the profile as processed, an echo of manufactured material, though others cautioned that rare natural chemistry could not be definitively ruled out. The nickel emission itself appeared to fade with solar distance, following an R to the 9th power decay, an abnormally steep drop-off that standard cometary models struggle to explain. Some researchers proposed that only a thin, volatile-rich veneer was being stripped away, exposing deeper layers as Atlas drew closer to the sun. Others wonder whether selective outgassing or even engineered release mechanisms could produce such a curve. The debate remains unresolved, but the stack of anomalies grows taller with each new observation. For now, the dossier remains incomplete. Imaging analysts, dynamical modelers, and spectroscopists all confront contradictions that natural comet models struggle to reconcile. Whether these paradoxes will dissolve with better data or deepen with new findings depends entirely on the next round of observations. Every anomaly adds weight to the argument that Atlas is not just another icy wanderer. The question hanging over the field: are these signals of nature's extremes or hints of something engineered? October 3rd, 2025, is circled on every mission planner's calendar. On that day, 3I/Atlas sweeps past Mars at a distance of 29 million kilometers, a margin that, for planetary science, offers a fleeting but critical observational window. Mars orbiters, including NASA's Mars Reconnaissance Orbiter and ESA's Trace Gas Orbiter, face a formidable challenge: capture high-resolution images of an object barely 5 to 7 kilometers wide moving against a backdrop of deep space. Technical teams have run extensive simulations, factoring the angular size, less than 100th of a pixel even for the sharpest cameras. HiRISE, the most powerful imager at Mars, achieves resolution of just 0.3 meters per pixel at close range on the Martian surface. But at this distance, 3I/Atlas shrinks to near invisibility. The planners acknowledge this limitation, yet the opportunity is too rare to ignore. For ground and trollers, the calculus extends beyond mere resolution. Tracking a fast-moving, dim target from orbit requires precise ephemeris data and split-second timing. Any detection, even as a faint point source, could constrain the object's position, velocity, or reveal unexpected activity, jets, fragmentation, or precursor debris. The imaging window lasts only hours. Data downlink schedules have been cleared, and real-time analysis teams stand ready to process whatever data returns. Meanwhile, proposals circulate for more ambitious retargeting options. Juno, currently looping through Jupiter's magnetosphere, has been flagged as a potential asset for a March 2026 intercept, should its trajectory and fuel budget permit. Mission engineers carefully weigh the risks. Juno's camera suite, designed for auroral and atmospheric imaging, lacks the sensitivity to resolve a small, distant interstellar object. ESA's JUICE and NASA's Europa Clipper face similar limitations. At 29 million kilometers, their best cameras would render a nucleus smaller than a 30th of a pixel, and any coma or jets would blur into noise. The operational verdict is blunt. No current spacecraft can deliver resolved imagery at this range. Attention shifts to the Galileo project and ground-based telescopes. Adaptive optics arrays and rapid response photometry offer the best possibility for detecting outbursts or directional jets, especially if coordinated with the Mars flyby. The criteria are strict. A meaningful detection would show asymmetry, jets aligned with the orbital axis, or evidence of structured fragments, clues that could distinguish a natural comet from something engineered. For now, the focus centers on collecting every possible photon before the object slips further from reach. The October 3rd window is narrow, the technical odds are long, but the potential payoff, a direct glimpse at the most massive interstellar visitor on record, keeps every console active through the night. October 29th draws a hard boundary across the calendar. On that day, 3i/Atlas disappears behind the sun, lost in the overwhelming glare, beyond the reach of every Earth-based telescope. The blackout is absolute. Even space telescopes, Hubble and the James Webb Space Telescope, are forced to wait. Their safety protocols prohibit any attempt to observe so close to the solar furnace. The practical result is a silence that stretches from late October into early December, a gap occurring precisely when the story reaches its most critical juncture. Propulsion specialists have weighed in with calculations that have become central to the ongoing debate. If 3i/Atlas were to perform a maneuver during the solar conjunction, the timing could not be better orchestrated. The orbit effect, a principle well known to every interplanetary mission designer, allows for a massive change in velocity, 30 to 40 kilometers per second in theory, if a burn is executed at perihelion, the closest approach to the sun. For a natural comet, such a maneuver is physically impossible. For a probe, however, the blackout provides perfect cover. No instrument on or near Earth can track a trajectory change in real time during solar conjunction. Only after the object reemerges weeks later can its orbit be remeasured and any deviation detected. The decisive test arrives in late November or December, when dynamicists will fit the new trajectory to every available observation. A match to the pre-blackout path would favor natural explanations. Any significant deviation, especially one requiring a high delta V, would force a fundamental reconsideration of every prior assumption. SETI directors and risk analysts now frame the situation as a yellow alert scenario. The stakes are transparent. If Atlas emerges on a shifted orbit, the case for artificial intervention strengthens considerably. If it resumes its predicted path, the anomaly stack diminishes, and the weight of evidence returns to rare but natural processes. Data release protocols are already established. Observatory teams have pledged to share positional updates in real time, minimizing the risk of rumor or misinterpretation. For now, the scientific community waits. Instruments idle as the object passes through its period of maximum uncertainty. The outcome, confirmation or refutation, will define the narrative for years to come. Yet no direct evidence conclusively links 3i/Atlas to an artificial origin, and many observations remain unverified or classified as preliminary. As missions prepare for the October 3rd Mars flyby and the October 29th solar occultation, The testable claims stand clear and unambiguous. Forthcoming data will determine whether this is merely a unique comet or something genuinely unprecedented. For now, the WOW signal and 3i/Atlas remain an open scientific question, grounded in numbers and awaiting answers. The combination of statistical improbabilities, physical anomalies, and chemical mysteries creates a compelling case for continued investigation. Whether we are witnessing the most elaborate cosmic coincidence in recorded history, or the first tangible evidence of extraterrestrial technology may soon be answered. The universe, as always, keeps its secrets closely guarded until the moment of revelation. October 3rd, 2025, 1437 Universal Time Coordinated. Mission control at NASA's Jet Propulsion Laboratory falls into an expectant hush as the Mars Reconnaissance Orbiter completes its final alignment sequence. The spacecraft high-rise camera, pushed beyond its designed operational envelope, begins its rapid-fire imaging sequence. Every engineer in the room knows the odds. Capturing a 6-kilometer object at 29 million kilometers is like photographing a grain of sand from across the Grand Canyon. The first data packets arrive 18 minutes later, traveling at light speed from Mars to Earth. Initial processing shows nothing, just the expected star field, cold and indifferent. Then, on the 47 frame, image analyst Dr. Sarachin freezes. A pixel cluster, barely 3 units wide, shows an albedo spike inconsistent with background stars. She runs the enhancement algorithm once, then twice, refusing to trust her own eyes. "We have something," she announces, her voice carefully controlled. Bearing matches predicted ephemeris to within 0.2 arcseconds. The room erupts in controlled chaos. Within minutes, ESA's trace gas orbiter confirms the detection from a different angle. But it's what the spectroscopic instruments capture that sends shockwaves through the facility. A brief flash, lasting only 2.3 seconds, in the infrared spectrum. The signature is unmistakable. A thermal bloom consistent with a high-energy event, not a natural outgassing, not a fragment breaking away. Something else. Dr. Marcus Webb, the mission's chief dynamicist, runs the numbers 3 times before speaking. If that thermal signature is accurate, he says slowly, we're looking at approximately 40 megajoules of directed energy. That's... He pauses, choosing his words carefully. That's an active process. The data is immediately classified as preliminary, but word leaks within hours. SETI observatories around the globe swing their dishes toward the coordinates. The Allen Telescope Array, the Parkes Observatory in Australia, even China's Fast Telescope, all listening, all searching for any whisper of electromagnetic activity. For 72 hours, the world's radio astronomers maintain an unprecedented vigil. Nothing, silence, but the thermal anomaly, captured by 2 independent spacecraft, remains unexplained. Natural explanations are proposed. A massive ice pocket suddenly exposed to sunlight, a methane geyser triggered by tidal stress, even a collision with interplanetary debris. Each hypothesis is tested and found wanting. The energy release is too focused, too brief, too precisely timed with the Mars approach. As October advances toward the solar conjunction, observatories coordinate a final intensive study campaign. The Hubble Space Telescope, granted emergency observation time, captures the last clear images before Atlas plunges into the sun's glare. The photographs reveal something that sends Avi Loeb's team scrambling to revise their models. The anti-tail has grown, not gradually, as models predict, but in discrete jumps. Frame-by-frame analysis shows the structure extending in pulses, measured, almost rhythmic. Every 6.7 hours, like clockwork, the forward-facing plume brightens and extends. Spectroscopic analysis of these bursts shows the same nickel-dominant signature, but now with an addition that makes no sense in conventional cometary science: organized spectral patterns that repeat with mathematical precision. Dr. Elena Sokolova, a radio astronomer with 30 years of SETI experience, runs the spectral data through pattern recognition algorithms designed to detect non-random signals. The results appear on her screen at 3 a.m. on October 24th. She stares at them for 20 minutes, then reaches for the phone to call the SETI Institute's director. "The spectral variations," she says without preamble, They're not random. They're following a prime number sequence. 2, 3, 5, 7, 11, 13, 17. It repeats every 4 cycles, then starts again. The director is silent for a long moment. How confident are you? 97%. I've run it through every filter, every noise correction algorithm we have. Either this is the most extraordinary coincidence in observational astronomy, or she trails off, unable to complete the sentence. Or we're looking at a deliberate signal, he finishes for her. The data is verified by 3 independent teams over the next 48 hours. By October 28th, the scientific community is fracturing into camps. Skeptics argue for unknown natural phenomena, citing the vast catalog of cosmic processes still poorly understood. Others, more cautiously, suggest that the evidence has crossed a threshold that demands consideration of artificial origins. And then, on October 29th at 6:14 Universal Time Coordinated, 3I/Atlas disappears behind the sun. The silence during solar conjunction is maddening. Astronomers, journalists, government officials, and millions of curious citizens wait. Social media explodes with speculation, conspiracy theories, and genuine scientific debate. The story dominates news cycles worldwide. Religious leaders offer interpretations. Philosophers debate implications. World governments quietly convene expert panels, preparing contingency analyses for scenarios they never seriously expected to confront. At the Arecibo Observatory, recently restored to limited operational capacity, a small team maintains a constant listening watch on a last known trajectory vector of 3I/Atlas, hoping that any signal might refract around the solar corona enough to be detected. It's a long shot, based on physics that are theoretical at best. But they listen anyway, recording terabytes of data for later analysis. On November 18th, something extraordinary happens. A graduate student named James Park, conducting routine analysis of the archived data from November 2nd, 2 weeks into blackout, notices an anomaly. A brief chirp in the 1,420 megahertz band, lasting exactly 72 seconds, buried in what everyone assumed was solar noise. He almost dismisses it as interference. But something about the pattern nags at him. He runs it through the same filter used to analyze the original WOW signal from 1977. The match is not exact, but it's close. Disturbingly close. The signal-to-noise ratio is lower, the frequency slightly drifted, but the characteristic pattern, the rise and fall, the duration, the channel distribution, echoes the original detection with uncanny fidelity. Park escalates immediately. Within hours, teams are tearing through the archives, searching for any other anomalies during conjunction period. They find 2 more, brief bursts on November 5th and November 11th, each lasting 72 seconds, each at frequencies offset from 1420 megahertz by predictable intervals following the same prime number sequence observed in the spectral variations. The implications are staggering. If these signals are real, if they're connected to 3I/Atlas, then the object was communicating during solar conjunction, when it knew it couldn't be directly observed. The signals weren't aimed at Earth. They were aimed to the sun's corona, using the star itself as either a relay or a shield, depending on interpretation. December 8th, 2025. The European Southern Observatory's very large telescope in Chile achieves first light on 3I/Atlas as it emerges from behind the sun. Within minutes, the initial positional data streams to calculation centers worldwide. Dynamicists begin the orbital reconstruction, comparing the new trajectory to pre-conjunction predictions. Dr. Marcus Webb leads the analysis at JPL. His team has prepared for every scenario, run 10,000 simulations, debated every possible outcome. But when the numbers resolve on his screen, he experiences something he hasn't felt since his first day in graduate school. Genuine awe mixed with visceral unease. 3I/Atlas has changed course. The deviation is unmistakable. The object's velocity has increased by 31.4 kilometers per second, a delta V that would require either a massive rocket burn or gravitational assist from an object that doesn't exist in that region of space. The new trajectory is still bound by the sun's gravity, but the orbital parameters have shifted. Most significantly, the modified path now brings 3I/Atlas much closer to Earth during its outbound journey. The new perihelion, the closest approach to Earth, is calculated at 0.78 astronomical units, approximately 117 million kilometers. Close enough for detailed observation. Close enough for signals to be transmitted with relatively modest power requirements. Close enough to be deliberate. The announcement breaks simultaneously across scientific networks worldwide. Within hours, it dominates every media platform on Earth. The White House, the United Nations, and space agencies from every major nation issue carefully worded statements acknowledging trajectory change while cautioning against premature conclusions. But the numbers speak for themselves. Either 3I/Atlas is a natural object that performed an impossible maneuver, or it's something else entirely. As December advances into January 2026, 3I/Atlas becomes the most intensely studied object in human history. The modified trajectory brings it within range of Earth's most powerful instruments during late February and early March. Radio telescopes worldwide establish a coordinated observation network. The James Webb Space Telescope dedicates unprecedented time to spectroscopic analysis. Even military surveillance assets are quietly repurposed for continuous monitoring. On January 14th, the Allen Telescope Array detects the first confirmed electromagnetic emission directly from 3I/Atlas. It's not the powerful beacon that science fiction prepared us for. Instead, it's subtle, intermittent, and maddeningly complex. The signal operates across multiple frequencies simultaneously, shifting in patterns that resist simple decoding but demonstrate unmistakable structure. Dr. Sokolova leads the analysis effort, coordinating teams across 6 continents. The signals don't repeat like the WOW signal did, or rather, didn't. Instead, they evolve, building on previous transmissions in ways that suggest either testing of communication protocols or a deliberate attempt to establish a vocabulary. It's doing what we would do, Sokolov explains during a hastily convened press conference. If we encountered an unknown intelligence, we'd start with mathematics, with patterns they could recognize. We'd build complexity gradually. This is following that exact strategy. By February 1st, 3 separate research groups have identified what appear to be embedded coordinates within the signal structure. Not astronomical coordinates. Those are already known. These are pointing to specific positions on Earth. Specifically, to the location of the original Big Ear radio telescope site in Ohio, now demolished but still historically significant. To Arecibo in Puerto Rico. To FAST in China. To the Allen Telescope Array in California. It's pointing to the places where humans listen to the stars. February 28th, 2026. At 2147 Universal Time Coordinated, as 3I/Atlas reaches its closest approach to Earth, every major radio telescope on the planet detects a synchronized burst. Unlike previous transmissions, this one is powerful, clear, and structured in a way that even preliminary analysis reveals as intentional communication. The signal lasts for 14 minutes and 22 seconds. It's transmitted on multiple frequencies simultaneously, with built-in redundancy and error correction, hallmarks of engineered communication systems. Within hours, teams working independently around the world begin extracting the same information from the data. The transmission contains 3 distinct components. First, a mathematical primer. Basic arithmetic, geometry, and physical constants, establishing a common language of understanding. This portion takes 47 seconds and is recognized almost immediately as intentional communication. Second, a star map, not of unfamiliar constellations, but of our own galaxy as viewed from a position approximately 600 astronomical units from the Sun, along the trajectory 3I/Atlas followed inbound. The map shows markers, hundreds of them, scattered across the galactic disk. The meaning is debated, but the most compelling interpretation suggests waypoints or markers left by whatever intelligence sent 3I/Atlas. A trail of breadcrumbs leading back to an origin point near the galactic core. Third, and most remarkably, a data packet that takes teams 3 weeks to fully decode. It contains what appears to be a schematic, technical diagrams that, once properly interpreted, describe the basic principles of the propulsion system that allowed 3I/Atlas to change course during solar conjunction. The information is incomplete, tantalizing, like the first chapter of a textbook rather than a complete manual. But it's enough. Enough to prove that the technology exists. Enough to show that interstellar travel is not just theoretically possible, but practically achievable. At the end of the transmission, there is a signature, a brief burst that analysis reveals to be mathematically equivalent to the original WOW signal from 1977, compressed and repeated exactly 7 times. It's an answer. 49 years late, but an answer nonetheless. March 2026. The world struggles to process what has happened. 3i/Atlas continues outbound, its transmissions falling silent after the February 28 message. Tracking stations follow it as it climbs away from the sun, back toward the interstellar darkness from which it came. By late March, it's too distant for detailed observation, becoming once again just another point of light against the infinite dark. But everything has changed. The schematic data from the transmission launches 1,000 research projects. Engineers, physicists, and aerospace designers worldwide begin the monumental task of understanding the principles embedded in the message. Early analysis suggests technologies that don't violate known physics, but push the boundaries of what humanity considered possible. Fusion-based propulsion, electromagnetic field manipulation, energy storage systems operating on principles that are theoretically sound but practically beyond current engineering. It will take years, perhaps decades, to fully comprehend and potentially replicate these technologies. But for the first time in human history, we have a blueprint, incomplete, challenging, but real, for reaching the stars. Avi Loeb, vindicated yet somehow humbled by the confirmation, addresses a joint session of the United Nations in April. We asked if we were alone, he says, his voice carrying to billions listening worldwide. We have our answer. But more importantly, we've been given a gift, not technology handed to us freely, but knowledge that we must work to understand. It's an invitation to grow, to develop, to eventually join whatever community of intelligence exists among the stars. They sent a probe 600 astronomical units away and waited for us to develop radio technology, waited for us to be ready to receive their message. The question now is, what do we do with this knowledge? The debate rages on. Some argue for caution, warning of unknown motivations and potential risks. Others push for aggressive development of the technologies hinted at in the transmission. International coalitions form to coordinate research efforts. New treaties are drafted addressing humanity's approach to interstellar communication and eventual expansion beyond our solar system. Religious and philosophical communities grapple with the implications. Some find their faith strengthened, seeing the discovery as part of a grander creation. Others undergo crises of belief, their worldviews fundamentally challenged. Most find themselves somewhere in between, struggling to integrate this new reality into existing understanding. By late 2026, the star map from the transmission becomes a focus of intensive study. Astronomers begin the process of cataloging the marked locations, searching for any anomalies or signals from those coordinates. It's slow work. The galaxy is vast, and many of the markers point to regions hundreds or thousands of light years away. But in October 2026, exactly 1 year after the Mars encounter, a team using the James Webb Space Telescope detects something remarkable at one of the marked coordinates, a transiting object passing in front of a distant star, its light curves showing patterns inconsistent with natural planetary bodies. The signature suggests geometric structures, regular patterns, possible artificial construction. It's 734 light-years away, far beyond current reach, but now impossible to ignore. More discoveries follow. By early 2027, 7 of the marked locations show potential signs of artificial activity or anomalous structures. The evidence is preliminary, controversial, and debated, but mounting. The map, it seems, was pointing us toward neighbors, or at least toward evidence that we're part of a much larger community than we ever imagined. The WOW signal, that brief burst from August 1977, has been answered, but the answer has led only to larger questions. Who built 3i/Atlas? How long has this network of markers existed? Are there other probes like Atlas, waiting at distant coordinates for other civilizations to reach the technological threshold needed to detect them? And most tantalizingly, will we someday be ready to follow the map ourselves? The Artemis lunar base, now operating at full capacity, hosts a small ceremony, a new radio telescope array, built specifically for deep space communication, goes online. Its first operational task: transmit a response back along 3i/Atlas's trajectory. The message is simple, encoded using the mathematical primer from the Atlas transmission as a foundation. It contains basic information about Earth, our population, our level of technological development, our location, and current capabilities. But most importantly, it contains 3 words, translated into the mathematical language established by the contact. We received, we understand, we will reach. The transmission beams out into the darkness, traveling at the speed of light toward a destination 600 astronomical units away, the position 3i/Atlas occupied in 1977. It will take over 3 days for the signal to cover that distance. Whether anyone or anything is still there to receive it remains unknown. But for the first time in human history, we're not just listening to the universe.